Welcome back. In today's lecture, we are going to discuss on crystal structure, defects and deformation. So, you should know what is a crystal. A crystal is nothing but a 3D translatory periodic arrangements of atom. So, what is a lattice? A lattice is nothing but a 3D translationally periodic arrangement of points. So, this is the major difference between a crystal and a lattice. If the 3D the atoms are arranged 3D form, it is called as a crystal. If the points, okay, periodic arrangements of points are there, then it is called as a lattice. Okay, so crystal consists of a lattice plus motif. What is a motif? A motif is nothing but an atom or a group of atoms associated with each lattice point. So, lattice is a discrete array of points in 3D space such that every point has identical surroundings. Now, coming to cell, a cell is nothing but a finite representation of the infinite lattice. A cell is nothing but it is a parallelogram, maybe a 2D or a 3D with lattice points at their corners. If the lattice points are only at the corners, then the cell is called as a primitive. If there are lattice point in the cell other than the corners, they are called as non-primitives. So, we have to know about the lattice parameters. So, lattice parameters are the lengths of the three sides of the parallel pipe, that is A, B and C are designated as A, B and C, and the three angles between the sides are designated as alpha, beta and gamma. Okay, where A is the length parallel to the x axis and B is the length parallel to the y axis and C is the length parallel to z axis. Alpha is the angle between y and z, beta is the angle between z and x, and y is the angle between x and y. Now, coming to the Bravais space lattices. So, there are 14 Bravais space lattices available. So, Bravais is a scientist who has found out many unit cells based on space lattices. Conventionally, the final representation of the space lattice is done using a unit cell which show maximum possible symmetries with the smallest size. So, Bravais worked out with three different symmetries, that is translation, rotation and reflection. So, considering maximum symmetry and minimum size, Bravais concluded that there are 14 possible space lattices or unit cells to represent them. These belong to 7 crystal classes. Okay, you can see the several classes of unit cells. So, arrangement of the lattice point in the unit cell is given in the form of simple cubic structure, face centered cubic structure, body centered cubic structure, simple tetragonal structure, body centered tetragonal structure, hexagonal structure, simple orthorhombic, body centered orthorhombic, base centered orthorhombic, face centered orthorhombic, rhombohedral, simple monoclinic, base centered monoclinic and triclinic. Okay, these are the 14 Bravais lattice structure available. Okay, among these 14 Bravais lattice structure, so 3 are very important, okay, which is present in almost all the metals. Okay, simple cubic structure, FCC, BCC and HCP structures. FCC is nothing but face centered cubic structure, BCC is body centered cubic structure and HCP is hexagonal closed packed structure. Okay, you can see these are the basic examples how the arrangements of the atoms okay, in a rock salt structure. You can see the sodium and the chlorides, okay, how the atoms are arranged, sodium atoms and the chloride atoms are arranged, okay, in a rock salt structure. You can see another example, cesium chloride structure, where the cesium and the chlorides are arranged. Okay, so whereas the chlorides are arranged in all the corners and at the center there is one calcium atom. You can see another example, zinc blend structure. Okay, you can see the zinc and the sulfide, okay, which are arranged in various forms. Okay, so and another AMXP type crystal structure, okay, that is calcium fluoride. Okay, calcium fluoride, you can see calcium and the fluorides are arranged in the unit cell. Okay, another structure is a AMBN XP type crystal structure, that is titanium, beryllium and oxygen cells. Okay, you can see these are the atoms arranged like this one. Okay, you can see the diamond structure and also the graphite structure. Okay, the structure of C60 bulky ball structure, fullerene, that is 20 hexagonal and 12 pentagonal rings. Okay, nowadays you can see the carbon nanotubes play a major role in our research. Okay, you can see these are the single wall carbon nanotube and multi wall, pictures of single wall carbon nanotube and multi wall carbon nanotubes. Okay, so you can also see the graphene structure, how the atoms are arranged in the graphene structure and the carbon nanotube structures. Okay, so these are the basics. You know about you should know about the atomic packing factor, the coordinate number and atoms per unit cell. Okay, when you are studying about a unit cell, so atomic factor is nothing but the ratio between the volume of atoms in a unit cell divided by volume of the unit cell. Okay, so the formula for that one is A is equal to 2R into root 2. Okay, so you can see in a simple cubic structure, body center cubic structure and FCC structure, HCP structure, this coordination number, atoms per unit cell and atomic packing factor plays a major role. Okay, you can see the number of atoms in the unit cell is 4. In a BCC structure, the coordination number is 12 and atomic packing factor is 0.74, whereas in the another structure, FCP structure, number of atoms FCC structure, the number of atoms per unit cell is 2, the coordination number is 8 and atomic packing factor is 0.68. Now coming to the crystallographic direction, a crystallographic direction is defined as the line between the 2 points, okay, or a vector. The following steps are utilized in determination of the 3-dimensional indices. A vector of a convenient length is positioned such that it passes through the origin of the coordinate system. Any vector may be translated through the crystal lattice without alteration if parallelism is maintained. So the second point is the length of the vector projection on each of the 3 axes is determined. These are measured in terms of unit cell dimensions A, B and C. These 3 numbers are multiplied or divided by a common factor to reduce them to the smallest integer values. The 3 indices not separated by commas are enclosed in square brackets. They are designated as U, V and W. The U, V and W integers corresponding to the reduced projections along with X, Y and Z axis are respectively. Right. You can see these are the how the A, B, C and X, Y, Z are designated. Okay. So the projections on X, Y and Z are A by 2 and in Y axis it is B and Z axis it is C and 0. Okay. Projection in terms of A, B, C in X axis, Y axis, Z axis are half, 1, 0 and reduction X axis 1, Y axis 2 and Z axis 0. And this is how it is enclosed 1, 2, 0 in the form of a bracket. Okay. So the orientation of the planes of a crystal structure are represented in the form of in a similar manner. Okay. So again the unit cell is the basis which the 3 coordinate system. In all the hexagonal system, crystallographic planes are specified by 3 Miller indices H, K, L. Okay, right. So I am not going to go in depth into the crystallographic planes and the Miller indices because it is just a introduction about our topic. So I am skipping this one. Now we will go directly into our topic. Okay, defects, type of defects. Okay, so there are 4 types of defects. One is a point defect or a 0-dimensional defect. Second one is a line defect or 1-dimensional defect, and third one is planar or surface defects or 2-dimensional defects, and the fourth one is volume defects or 3-dimensional defects. We will see these types of defects one by one in detail. What is a defect? Okay, defect is nothing but if an atom is missing in a particular lattice point, it is called as a defect. Okay, or vacancy, it may be called as a vacancy. Okay, you can see the first diagram, the left hand side. In pure metals you can see the point defects can be further classified into a vacancy or a self interstitial. Okay, so you can see in pure metals a vacancy, that is pure metal only one type of atoms will be there. Okay, you can see this diagram, the left hand side. In alloys there are 2 types of vacancies, that is point defects, that are substitutional impurity and interstitial impurity. You should know what is an interstitial and substitutional impurity. Okay, what is a substitutional solid solution? Substitutional solid solution is nothing but, already we have discussed these things in the earlier lecture. The atoms. Okay, so there are 4 rules to form a substitutional solid solution. In the beginning class I told you, if you are mixing with one element with the other element, okay, if it is soluble completely, then it is called as completely soluble in nature. Okay, if it is not soluble, okay, so it will form a compound, right? So there are different soluble limit for each and every metal. For example, 20% of copper can be dissolved, 20% of gold can be dissolved in copper, whereas gold can dissolve only 10% of copper, like this. Okay, after it has dissolved, it will form as a new structure. Okay, so the gold and the copper will be forming with a new structure. Okay, like this. So, you should know what is a substitutional solid solution. Substitutional solid solution is solution in which the atoms of the substitute atoms, solute atom and the solvent atom will be of the almost in the same size. There are 4 rules defined by Hume Rothery. Hume Rothery is a scientist who formulated the rules for forming a substitutional solid solution. Okay, so in that first factor is a crystal structure factor, relative size factor. The second point is relative size factor, third one is a relative valence factor, and fourth one is a chemical affinity factor. These are the 4 rules. Okay, so you can see these diagrams which shows a substitutional solid solution. You can see a gap between the 4 atoms, okay, that is called as interstitial spaces. For example, if you take an iron and a carbon, okay, the iron atoms are larger in size, whereas the carbon atoms are considered as impure atoms, which will occupy the gap between the 4 atoms. That is this is the lattice point in between the 2 lattice lines. You can see there are some interstitial spaces where the atoms will occupy. Okay, so when we are discussing on the mechanism of strengthening, we will discuss those things. Okay, now you should know what is substitutional impurity and interstitial impurity. Okay, right. So point defects or 0 dimension defect can be further classified into a vacancy or self interstitial in case of pure metal, whereas in alloys they are substitutional impurity or interstitial impurity. Okay, so you can see a point is given here, it is important in strengthening. Okay, right. So then coming to the next one, line defects or one dimensional defects. Line defects are one dimensional defect. You can see they are classified into edge dislocation and screw dislocation. Edge dislocation, you can see the first diagram. Okay, so the edges alone will be dislocating. Okay, if the atoms, as I said in the substitution atoms, okay, if the atoms of solute atoms is more than the solvent atom, the size of the solute atom is more than the solvent atom, it will it will form a barrel distortion. If the size of the solute atom is lesser than the solvent atom, then it will form of a pincushion distortion. That is nothing but barrel distortion means this will go outside, and pincushion distortion means it will come inside. Okay, like this one. Okay, you can see this kind of changes is called as a dislocation. Okay, dislocation, or it is considered as a defect. Okay, it is considered as a defect. Okay, so in plastic, when material are subjected to some to tensile forces. Okay, when a load is applied to a material, then the material is subjected to dislocation. Okay, the dislocation may be either screw dislocation or edge dislocation. Those things you will study in detail in the unit 2, where we are going to discuss about the tensile test. Okay, so the main reason for plastic deformation is, one is called as a slip, another one is a twinning. Okay, so the slip causes edge dislocation causes slip, and twinning is caused due to screw dislocation. Okay, these kind of dislocations are the effect of the application of the load on the material. Okay, you can see how the twins are being formed. Okay, you can see this is the microstructure okay, of a material. Okay, in which you can see the twins. Okay, twins is nothing but a mirror image of the lattice structure will be formed on the opposite direction, in between there will be a plane. Okay, right. We will discuss this detail in the when we are discussing about the plastic deformation. Right. The third type of defect is a planar or a surface defects or a 2-dimensional defect. You can see this is the stacking. Okay, stacking of the atoms one over the other. Okay, so you can see you can see how the stacking fault can be further divided into perfect stacking, extrinsic stacking, and intrinsic stacking. Okay, extrinsic and intrinsic stacking. You can see this layer of A atom, okay, followed by B layer, followed by A layer, B layer, A layer. Like this, the atoms will be stacked like this one. Okay, in an alloy. That is, for example, solute atom, substitute solvent atom, solute atom, solvent atom, solute atom, solvent atom, like this. Okay, so if it is an eccentric stacking fault, you can see in the B. Okay, there is a vacant place at the edges. Okay, center there is a presence of atom, at the edges there are vacancies, whereas in case of intrinsic shackling fault you can see there is a vacancy at the center, the edges are filled with the atoms. Okay. So similarly, if the alloying element, more alloying element is added, okay, apart from A and B, one more alloying element is added C, then the atoms will be stacked like this on A B C A B C A B C like that, or B A C B A C or C B A like that. Okay. So they can also see the extrinsic shackling fault which is where there are two vacant places at the edges. Okay, and also you can see the vacancy at the center in case of intrinsic shackling fault. Okay, right. The next type of planar defect is grain boundary defects. Okay, grain boundary defects. You can see the grain boundaries. This is the diagram, schematic diagram showing low and high angle grain boundaries and adjacent atom position. Okay, you can see based on the cooling of the metals. Okay, the rate of cooling defines the formation of the high angle and the low angle grain boundaries. Okay, you can see the first diagram shows how the solidification takes place, that is dendrites are formed. Okay, and slowly the atoms are united together to form a cell. Okay, unit cell. Okay, so on the as the cooling proceeds, you can see all the atoms are stacked in one places like A B C like that, it will be stacked, and after occupying these places it will form a grain boundary like this. The third stage where the complete unit cell is formed, and the fourth stage you can see these are the boundaries. Okay, after the house is filled, okay, they will form a boundary in different directions. So based upon the time of cooling, okay, you can see these kind of grain structures. Okay, low angle and high angle grain boundary. If the process is slow cooling, then you can see a orderly arrangement of atoms and fine grain structures. Okay, whereas if your cooling rate is fast, you can get a coarse grain structure because you are not giving a sufficient time for the atoms to sit in its position. Okay, so this is also considered as a planar defects. Okay, then fourth type of defect is a volume defects or three-dimensional defects. They includes precipitates which are small volumes or different crystal structures, and also include large voids or inclusion of the second phase particles. Okay, so now coming to the next topic, that is dislocations. What is a dislocation? A dislocation are nothing but a line defect that exists in a metal. Okay, so usually the dislocations are specified by means of the symbols. Okay, you can see this is a perpendicular symbol. Okay, there are two types of dislocation. One is called as edge dislocation and screw dislocation, what we have discussed in the line defects. Okay, edge dislocation and screw dislocations. The dislocation density is annealed metals is normally 10 power 6 per centimeter square. Okay, you can see the plastic deformation of crystal by shear. You can see how the plastic deformation takes place. When a plastic deformation takes place, when a metal is loaded, okay, tensile load is applied on both sides. Okay, so the driver for the tensile force is a shear force. Okay, shear stress, okay, which acts on the surface, that is an equal and opposite stress which act on the surface. So the driver for this tensile force is shear stress. Okay, only the shear stress will starts to move. Okay, like shuffling a card. Okay, when we shuffle a deck of cards, okay, our right hand side will be moving towards us, and the left hand side left hand will be moving opposite direction. Okay, see, that is called as shear stress. Okay, similar to the shear stress, see the atoms will be moving. This movement is called as a dislocation. So the dislocation can be classified into edge dislocation and screw dislocation. Already we have discussed this, how the edge and screw dislocation. Okay, the dislocations are caused by means of the vector called as a Burger vector. So a dislocation is associated with the two vectors. One vector is called as a Burgers vector, which is represented by B vector, and another vector is nothing but a unit tangent vector along the dislocation line. Okay, so normally this Burgers vector will act in the place perpendicular to the tangent vector. You can see this one. The Burger vector is a vector often denoted B that represents the magnitude and direction of the lattice distortion resulting from a dislocation in a crystal structure. You can see this is the line vector. Okay, so as I told you, this is a deck of cards. Okay, one card will be facing towards you, moving towards you, another card will be moving against you. Okay, that kind of dislocation is a edge dislocation. Okay, see how the vectors are acting. The Burgers vector will be acting along the line perpendicular to the line vector, okay, along the line perpendicular to the line vector, okay, whereas in case of screw dislocation you can see, okay, this tangent line is somewhere different. Why means because in the screw dislocation, okay, due to some twisting moment, this kind of action takes place. The line vector changes its direction, whereas the burger vector remains the same, okay, as in the case of edge dislocation. Okay, dislocation moves along a slip plane in the slip direction perpendicular to the dislocation line. The slip direction is same as the burger vector's direction. Okay, slip direction, the direction of the movement of the atoms, okay, due to the action of shear stress is the slip direction. Okay, so the burger's vector direction is also similar to that of a slip direction. Okay, so you can see a diagram which illustrates the stress field of a dislocation, regions of compression and regions of tension. Okay, you can see the black color which is a regions of compression, whereas in the bottom you can see red color which is a regions of tension force. Okay, so dislocation of material classes, for example you can see how the dislocation takes place in a copper and aluminum. Okay, so dislocation motion is ECS, that is non-directional bonding. Okay, close packed direction. In case of metals, dislocation motion is very much easier. Okay, easily you can move the atoms. Okay, non-directional bonding, they are close packed direction for slip. Whereas if you go to a covalent ceramic bond, okay, you can see this is the covalent bonds where the examples are silicon and diamond. The dislocation motion is difficult because all atoms are attached to each and every one. Okay, but here you can see the atoms are independent. Okay, so dislocation is easy. Okay, so the motion is difficult in case of ceramics. So directional bond, it has a directional bonding. So you can see the ions ceramics and sodium chloride, the motion is again difficult. Okay, you can see positive charge ions followed by a negative charged ion. Okay, like this. So the motion is difficult. So need to avoid nearest neighbor like sign minus and plus. So dislocation motion and plastic deformation, how they are related to each other. So metals plastic deformation occurs by slip, that is an edge dislocation. Extra half plane of the atom slides over the adjacent plane half plane of the atoms, that is already we have discussed. Okay, you can see this is the actually the tensile force act at the center, whereas the shear force act at the surface of the atoms. Okay, so you can see the edge dislocation line, you can see this dislocation how it is being moved. If there is an atom which is, if the dislocation motion is easy, okay, there is no barrier, then easily the slip will takes place. Okay, when there is a barrier in between, okay, then it has to change its direction, okay, so it will climb and change its path. Okay, the slip direction will be changing in the another direction, due to that this straight line is crossed into a different passage. You can see this one A. Okay, so the slip is like this one, it is coming here. Okay, after that, since due to the barrier there, it will take a different direction and it will move on based on the application of the tensile stress. If dislocation can't move, plastic deformation doesn't occur. This is the one important point you should note. Okay, how a dislocation can be moving, you can see like a caterpillar. Okay, so a caterpillar, so this is the dislocation. So as the caterpillar, when it starts to move, the dislocation starts to move. Okay, so after it passes one stage, okay, you can see the dislocation keep on moving like this, from second position it has come to fourth position, then fifth position, sixth position, like that it will move on. Now we can see the distorted structure. Okay, distorted structure, okay, due to the application of the shear forces. Okay, so this is the microstructure view of a metal which has some dislocations. Okay, so motion of dislocations, there are two types of motion of a dislocation are possible. One is dislocation glide and climb. Okay, this topic is very important. First we can consider a glide motion. Dislocation may move over external applied force, okay, resulting in stress inside the material, often called as an applied stress. At the local level, shear stress on the slip plane can only drive dislocation. Okay, so dislocation, to drive a dislocation, if the dislocation has to move, okay, so who is the driver? the driver is nothing but the Pearl Navarro stress. Okay, the minimum stress required to move a dislocation is called as a Pearl's Navarro stress. Okay, so Pearl's Navarro stress or Pearl stress or the lattice friction stress, that is the externally applied stress, may even be purely tensile, but on the slip plane shear stress must act in order to move the dislocations. Okay, so the driver for the dislocation to move is Pearl's Navarro stress, that is a minimum stress required to move the dislocation. Okay, so the driver for the shear stress is Pearl's Navarro stress. Okay, so the driver for tensile stress is shear stress. Okay, now even though we are applying the tensile stress, okay, so the tensile stress, the tensile force cannot move unless there is a dislocation. So for dislocation to move, there Pearl's Navarro stress should come into act, that is a minimum stress required to move the dislocation. When the dislocation starts to move, shear stress come into action, then this shear stress will have the driver for tensile stress. Okay, so as the tensile force increases, okay, these stresses, Pearl's Navarro stress and slip, that is shear stress, will accumulate and make the material to deform. Okay, so dislocation may also move under the influence of other stress fields. Okay, so dislocation attracted to free surface and move because of this attraction. This force is called as an image force. In any case, the Pearl stress must exceed from the for the dislocation to move, unless otherwise the Pearl stress, okay, is exceeded by other stress, the Pearl stress will not come into picture. Okay, the value of Pearl stress different for both edge and screw dislocation. The first step of plastic deformation can be considered as the step created with the dislocation moves and leaves the crystals. Okay, so now coming to the motion of edge dislocation, they can be conservative or non-conservative, that is they can be classified into glide and climb. Motion of dislocation on the slip plane, motion of dislocation perpendicular to the slip plane, whereas the conservative motion is motion of dislocation takes place on the slip plane, non-conservative climb is nothing but motion of dislocation perpendicular to the slip plane. Okay, so for edge dislocation, B is perpendicular to T, they define a plane, the slip plane. Okay, climb involves addition or subtraction of row of atoms on below the half plane. This can be illustrated by this diagrams. You can see the first diagram which is on the left. Okay, you can see this is the dislocation motion. Okay, this is the dislocation motion, this is the slip plane. Okay, this is the dislocation line into the plane, right? So if there is a pinning point, okay, so it will see, you can see this is the normal diagram which illustrates the dislocation line, pinning point on the slip plane. Now you can see, now the dislocation is moving from the extra half plane, it is moving here. Okay, then there is a barrier. Okay, so that it cannot it push the barrier. Okay, so you need lot of forces. Okay, instead of what happens, it climbs. Okay, it climbs the barrier and starts to pass in the new slip plane. Okay, so continuous motion of dislocation, that is called as a climb. This process is called as climb. Okay, so the motion of dislocation is being arrested due to some hindrance, so that it climbs and move on the new slip plane. Okay, so dislocation leaving the slip plane. Okay, so there are two types of dislocation I told you. One is called as a slip, another one is a twinning. Okay, we have discussed on slip plane. Okay, whereas the twin motion, okay, twinning motion, right? Suppose if it is moving on this one, the not only one layer of atom will be moving. Okay, so the entire layer of the atoms will be moving when due to the action of the tensile force. Okay, suppose the barrier is more, which it cannot climb. Okay, so the entire plane will be shifted. Okay, that is called as twinning. If the entire plane is shifted to a new plane, then it is called as a twinning motion. Okay, right. So dislocation leaving or climbing the slip plane can be classified into edge dislocation and screw dislocation, as we have discussed earlier. Okay, you can see this is how the climb of edge dislocation. Okay, it's a positive climb. If it is moving upwards, it is a positive climb. It is moving downwards, it is called as a negative climb. Okay, so cross slip, already I told you this one is twin motion. You can see if the barrier, okay, if the barrier is heavy, okay, so the entire plane of atoms will be shifting. Okay, shifting on a new plane. Okay, that's what it causes a mirror image on this side with the other opposite side. There is a difference, there is a in between these two mirror image there is a plane. Okay, entirely new plane. Okay, which causes the twinning dislocation. Okay, so the dislocation moving on slip plane 1, okay, or as the result shear stress the maximum slip plane. The figures below shows the cross slip of a screw dislocation line from slip plane 1 to slip plane 2. This may occur if the dislocation is pinned on slip plane 1. Okay, so dislocation is pinned here, it cannot move or climb or glide. Okay, so instead the entire layer of atoms will climb. Okay, will climb and it will pass through a new slip plane. Okay, that process is called as a pinning deformation. So with this we will stop our discussion for this lecture. Okay, the remaining lecture we will discuss in the next class. Thank you for your attention.